Hey everyone, let's take a look at section 4.4, L'Hopital's rule, our next topic. The last two sections, 4.3 and 4.5, were graphical applications of the derivative, right? We use the derivative to properly sketch a curve. Here, we're going to use the derivative to take limits, right? We're going back to limits. Now, remember before, when we were taking limits, stuff got tricky when we took the limit. We tried to take the limit. We tried to plug in x equals a into f of x, and we would get 0 over 0 or infinity over infinity, right? That's where we ran into some trouble. Remember, occasionally we would even get weird things like infinity minus infinity. We would have to do, common denominators, things like that. So anyway, the way that we would find the limits is we'd either factor, multiply by the conjugate and factor, common denominator, subtract the fractions and factor, etc. For infinity, we had to look at the leading term, etc. There was squeeze theorem. But what about a problem like this, with ln of x or e to the x or something? You can't use any of those techniques with a problem like this. Of course, you could look at the graph, but who wants to do that? So instead, we have to turn to another technique. It's actually a result called L'Hopital's rule. Okay? And it's now, by the way, proven by one of the Bernoulli brothers. I forget whom. But it says that suppose f and g are differentiable, and I guess we need to know that g of x does not equal 0 near a, right? So that we're not dividing by 0, right? Suppose that this limit gives the indeterminate form 0 over 0 or infinity over infinity. Then, here's the result. The limit as x approaches a of f of x over g of x equals the limit as x approaches, so let's write that a little bit better, the limit as x approaches a of f prime of x over g prime of x. So it turns out, if you take a limit and you're stuck with an indeterminate form, then just take the derivative of the top, take the derivative of the bottom, and try again. Maybe the limit will be easier. So let's prove this very quickly. I'm going to do the 0 over 0 case. The infinity over infinity case is just the inverse of this, right? It's just the opposite. All right. So I guess we'll say if f of a over g of a equals 0 over 0, or maybe I shouldn't even say equals, gives 0 over 0, then what do we really mean by that? What does it mean that it gives an indeterminate form? It means that f of a equals g of a, which equals 0, right? That's what we're really saying. And that's actually how the book presents the theorem. It says if f and g are differentiable, g prime does not equal 0, and f of a equals g of a equals 0, then blah, 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 okay? So anyway, what does this give us? This means that the limit as x approaches a of f of x over g of x equals, well, I guess since f of a and g of a equals 0, we can do one of the oldest tricks in the book and just kind of subtract 0. See how I'm subtracting 0 from the top and the bottom? All right, just like that, right? Because these are 0, right? 0. We're not subtracting anything. We're not adding anything. And I guess, we could also do, I suppose this is okay, is we could multiply the top and the bottom by x minus a, right? It's okay to do this as long as we're doing it to the top and the bottom, right? We're not changing the fraction or anything like that. We're just changing the way it looks, right? Right, and so then we get this. I know that we're making this uglier and uglier. Well, that should be a g of x, sorry. Right? Now, why do we do that? Well, I guess one more thing we could do, assuming these limits exist, which, spoiler alert, they do, we could even say that the quotient of the limit of the quotient is the quotient of the limits. And maybe at this point, right, this is using limit laws, right? And maybe at this point, we should note that that's just another way of saying that like this is just the, oh shoot, sorry. That this is really just the derivative, right, of f at a, right? And this is the, and this is just the derivative of g at a, right? So what we can say is that, well, I guess then this is equal to limit as x approaches a of f prime of x over g prime of x. Okay? And that is our proof. All right? Now remember, you don't need to know this, okay? You can skip ahead if you want. You can just skip ahead. So if we look at example 2, and we do this example, right? This is the one that we had asked before, right? How do we do this, okay? Well, let's see. Limit as x approaches infinity, ln of x over x. Well, if you just try to straight up take the limit, right, plug stuff in, you get the indeterminate form infinity over infinity. Remember, we didn't prove this, but it's a completely analogous. You just do 1 over each of them, right? So anyway, you get that, and then we say, okay, using L'Hopital's rule, which I'll just denote with an LH, we get that this equals the limit as h approaches infinity of 1 over x over 1. You see how I just took the derivative of the top and the derivative of the bottom? All right, that's all I did. Right? So anyway, you do this, and I think this is clear, just to totally draw this, like to make this crystal clear, right? This is just that. And then we just get an answer of 0, right? So we really needed L'Hopital's rule to do that. Now, just to make sure, we had to check that we had an indeterminate form. L'Hopital's rule does not necessarily work if you don't have an indeterminate form. So you have to test that out, okay? So, by the way, you might see this again in Calc 2, perhaps. Right. I wanted to do this. Change this to 0, right? Do not make it infinity. I mean, you could make it infinity. It's still an interesting problem, but I think it's a less interesting problem. I want to make this 0. Oh, let me just really get that out of there. All right, so anyway, we have this. Limit as x approaches 0, e to the x minus 1 minus x. Again, if you're taking Calc 2, then you might see this problem again. I hope you do, because when you do, you'll be learning it in the context of something called Taylor series or Maclaurin series. So this looks all gross. Let me try this one more time. Much better. Anyway, if we try to take the limit, then we get 0 over 0. All right? E to the 0 minus 1 minus 0, 0, 0, bottom is 0. So we get to use L'Hopital's rule, okay? We keep writing the limit as x approaches 0. Do not stop writing that, okay? We have e to the x minus 1, and then the bottom is 2x, right? Now what happens if we take the limit? Well, we actually still get 0 over 0. So that's not going to work. So what do we do? Well, at this point, we can actually just use L'Hopital's rule again, right? There's nothing saying we can't use it. So let's do it again. Take the derivative of the top and the derivative of the bottom again, and you get this. And at this point, you see that the limit is, in fact, 1/2. Okay, so that's your answer. So sometimes you might need to do L'Hopital's rule twice. All right. Number 2. Now this one's a little bit trickier, right? If you just try to take the limit. You're going to get infinity over infinity. Now this is an interesting one, because if you know the graph of ln of x and you know the graph of the square root of x, they both have this kind of a shape to it, right? They're both always concave down. So it's a question of which grows faster, which grows slower. right? But anyway, we have an indeterminate form, so we get to use L'Hopital's rule. So we're going to take the derivative of the top, derivative of the bottom. We're going to get 1, let me shift this down a little bit. 1 over x on the top, 1/2, so it's 1/2 x to the negative 1/2 on the bottom, which is 1 over 2 root x on the bottom. Now, at this point, you could try to take the limit. You're going to get 0 over 0. And you might think, oh, I'm going to do L'Hopital's rule again. But no, that's just going to dig you into a deeper and deeper hole. What you really need to do is simplify. Right? Maybe I'll just put this, yeah, whatever. We'll put this over here. And we'll get that equals the limit as x approaches infinity. And if you don't believe me, right, just sort of what we're going to do is take the bottom, put up on the top, take the top, take the top, and put it down on the bottom, so to speak. We're going to get 2 root x over x. Now, pause the video if you don't see that simplification, because that is how it works, right? Just maybe I'll write in red over here. A over b divided by c over d equals a over b times the reciprocal, d over c. Okay? That's how we get it. So anyway, at this point, we're going to divide the top and the bottom by the square root of x. And at this point, we see that our answer is 0. Okay? So that's what we're getting, right? Turns out that square root of x increases faster than ln of x because, you know, just the bottom increases quicker than the top. So you get 0. All right? Now, pause the video and try to do number 3. All right? You have an answer? So here's my answer. So I'm getting 1/11. No. Negative 1/11. Right? Is that what you got? Or did you get something else, like 3/8? If you got 3/8, then you are incorrect. You do not get to use the L'Hopital's rule if you're not getting 0 over 0 or infinity over infinity. So please be careful. Always verify that you are, in fact, able to use L'Hopital's rule, because sometimes you might get the wrong answer. So it turns out that L'Hopital's rule is very effective at solving limits with indeterminate forms. These are just some of the indeterminate forms, pretty much all the ones that we'll cover that you can use L'Hopital's rule to cover, along with our 0 over 0, infinity over infinity, right? All those different expressions that you see right here are other kinds of indeterminate form. Now, the thing is, L'Hopital's rule works only with 0 over 0, infinity over infinity. If you have something like 0 times infinity, then you don't get to use L'Hopital's rule right off the bat. You have to change it into a fraction. So let's see how to do that. Limit as x approaches 0 of x times ln of x. Well, if you try to take the limit, you get 0 times, and remember, ln of 0, you can't really plug in 0, but as x approaches 0 from the right, which we should really be writing, actually, this really should be a plus sign, right? It approaches negative infinity, right? ln of x approaches negative infinity as x approaches 0 from the right. All right, so anyway, we're going to get the limit as x approaches 0 of, now remember, we can't use L'Hopital's rule yet. But what we can do, and this is kind of sneaky, is instead of multiplying by x, divide by 1 over x. Now we have negative infinity over infinity, right? And now we can use L'Hopital's rule. All right, and so we wind up getting 1 over x on the top negative 1 over x squared on the bottom. Don't forget about that negative sign, although I'm not sure it's going to matter in this case. And then just do a bit more simplification, right? Just like the last one. Multiply by that reciprocal. And we get, it doesn't really matter where you stick the negative sign. Negative x squared over x. Divide the top and the bottom by x. We get negative x over 1, and then that equals 0. So in the fight between x approaching 0 and, ln of x approaching negative infinity, well, I guess the x equals 0 part wins, so to speak. So there's that. All right. Next up, number 5, right? Try that on your own. And then unpause the video when you get an answer, right? So anyway, same sort of thing. Limit as x approaches infinity, x tangent of 1 over x. And we do this, and we get infinity times, now, tangent of 0 is 0, because sine of 0 is 0, cosine of 0 is 1. All right, so we're approaching infinity times 0. We can't use L'Hopital's rule yet, so we, again, divide by 1 over x. And now we get 0 over 0, and now we can use L'Hopital's rule. And the cool thing about this is that, note that we have to use the chain rule on the top. Now, what's so cool about using the chain rule? Well, it's that the derivative of 1 over x on the top equals the derivative of 1 over x on the bottom. So they cancel out quite nicely. You like that, right? So we're just left with secant, oops, sorry, that's secant squared. I forgot to write the squared when that happened. Secant squared of, well, 1 over x approaches 0 as x gets large, right? What's secant squared of 0? It's 1 squared, which is 1. So the answer is 1. Okay? Now, we've got a couple more examples, right? In this case, right, we have an indeterminate form with differences. The limit as x approaches 1 of x over x minus 1 minus 1 over ln of x. Well, the problem with that is that you have infinity minus infinity, right? You got this 1 over 0 minus 1 over 0, right? No good. I remember when I first saw this, I said, oh, well, I guess the answer has to be 0, right? It's infinity minus anything minus itself is 0. But it's not, right? You can't use limit laws for this because these things don't approach infinity at the same rate. So their difference is not just going to be 0. So what we do, as you might guess, is we use a common denominator. So before any sort of calculus has occurred, we just get this as x ln of x minus x minus 1 all over the common denominator, x minus 1 ln of x. Okay? Now, how did I get that, by the way? If you didn't see that, I multiplied this by ln of x over ln of x, and I multiplied this by x minus 1 over x minus 1. Okay? So we get that. Now, at this point, if you do it out, you get 0 over 0. Note that ln of 1 is 0. Okay, so just remember that. So now we get to use L'Hopital's rule. But with this derivative, note that we've got a product rule on the top and the bottom, right? So you have 1 times ln of x minus x times 1 over x minus 1. Oh, geez. Looks like my mom has COVID. Awesome. And anyway, we're going to do the product rule on the bottom. 1 times ln of x plus x minus 1 times 1 over x. All right, and so that is what we've got. Now, we can simplify this a little bit. Oh, shoot, sorry, that should be a plus. That should be a plus that, okay? So anyway, when we do this out, we're going to get ln of x plus 1 minus 1, cancel, right? Because x times 1 over x Right? And we're allowed to do this, right? Because x is not 0. It's approaching 1. Even if it were approaching 0, we'd be fine, right? Anyway, so that goes away. And then we have ln of x plus, and then I guess this is x minus 1 over x. And then at this point, we can do it out, and we get 0 over 0. Oh my gosh. Right? Because ln of 1, remember, equals 0. 1 minus 1 over 1 equals 0. So annoying. Right, so anyway, we can take the derivative again. Now, one thing I'm going to do, you can just do the quotient rule for the x minus 1 over x, but one thing I'm going to do, screw it, I'll just do the quotient rule. You could write it as 1 minus 1 over x, might be a little easier, but whatever. We get 1 over x, and now the derivative of this, right, it's going to be low d high minus high d low all over low squared. Well, look what happens. The x's all cancel out. And you wind up with 1 over x over 1 over x plus 1 over x squared. Right? And then you just take this limit and you get 1/2. So that's our answer. So believe it or not, this limit equals 1/2. Not what I was expecting. So anyway, last type of problem that we're doing. And there are 2 examples of it. We want to find the limit as x approaches infinity of this guy. Now again, this is not a standard indeterminate form that we're used to, right? It's not 0 over 0 or infinity over infinity. It's a weird kind of 1 to the infinity kind of thing. All right? 1 to the infinity. Have we ever seen that before? I think we have, actually, believe it or not. Back when we defined e, remember. E to the, I should just say e is defined to be the limit as x approaches infinity of 1 plus 1 over x to the x. So you might imagine, you might guess that this answer is related to e. And you would be right. So in order to solve this problem, we're going to let y equal this. Okay? This is a little bit involved, but it's very formulaic, right? So ln of y, oh yeah, take the ln of both sides, right? Remember that sort of thing? Remember that nice little trick? We're busting it out again. Right? Now, little technicality that you don't need to know, but you just need to know that you can do this. Because ln and this guy right here are continuous functions, we're allowed to swap the ln with the limit. Right? And then that is gonna, is gonna lead to this. Right? So we brought the power down, right, because of our ln rules, right? Right, that's just an ln rules, remember. Ln of a to the b equals, b ln of a. Okay. So anyway, now that we have this, we can take the limit, and we get infinity times 0, right? Because this goes to 0. This goes to 1, which ln of 1 equals 0. Right? So we're going to get, well, I guess we can't use L'Hopital's rule, can we? Well, then I guess what we need to do is we need to do that trick, right, where maybe instead of dividing by x, leave the 5 up there, we divide by 1 over x. Now, at this point, we have 0 over 0. So at this point, we can finally use L'Hopital's rule. Now, the derivative of the top is a little bit involved, right? There's a bit of chain rule, right? But we're going to get, let me maybe bring this down a little bit, right? Okay, so we're going to get 5 times 1 over the inside times the derivative of the inside, which is negative 6 over x squared. The bottom is going to be negative 1 over x squared, right? We took the derivative of the top and the derivative of the bottom. And something kind of nice happens, right? The negative signs cancel out, the x squareds cancel out, the 1 over x squareds cancel out. And we're left with the limit as x approaches infinity of, I guess it's 30 over 1 plus 6 over x. And I guess that answer equals 30. So our answer is 30? I thought it had something to do with e to the x, or e, rather. Well, it actually does. And the answer is not actually 30. ln of y equals 30. So then what does y equal? E to the 30, right? ln of what number gives us 30? E to the 30th. So our answer is, in fact, e to the 30th. And by the way, just take a note. Oh, look at that. It's 30 is 6 times 5. I wonder if that's a coincidence. Well, maybe we should do one more problem. Really quickly, pause the video and try to figure out what the answer would be right now. Just guess what the answer would be. I think it's going to be e to the negative 4. But we can't just guess that, right? That's a needs improvement. We have to actually do it. So let's do it out. So I guess what we're going to do, actually, is we're going to take that. So ln of y equals ln. Well, I'm just going to skip that step and write the limit as x approaches infinity of ln, right? You can just stick the ln inside the limit every time because you know it's always going to work, right? And this equals the limit as x approaches infinity of 4x ln of 1 minus 1 over x. And then that's going to equal, right? By the way, again, I should have even mentioned we had like 1 over 1 to the infinity, right? If we tried to plug it in. At this point, we have infinity times 0. And so we're going to get the limit as x approaches infinity of 4 ln of 1 minus 1 over x. And then divided by 1 over x. Now we have 0 over 0. And so now we're going to get, now we can use L'Hopital's rule, right? Okay, so then we get 4 times 1, 4 times 1 over 1 minus 1 over x. And then times the derivative of the top, which is actually 1 over x squared, right? Because it's negative, 1 over x squared. And the bottom is negative 1 over x squared. And we see where we're getting our negative from, right? The x squareds cancel, but the negative does not. So we wind up with the limit as x approaches infinity of negative 4 over 1 minus 1 over x. And that's negative 4. So again, ln of y equals negative 4. So y equals e to the negative 4. And that's our answer.